Throughout human history, warfare has driven some of the most innovative and sometimes downright bizarre inventions ever conceived. When nations face existential threats, military minds push beyond conventional thinking, exploring every possible advantage, no matter how strange or improbable it might seem. The weapons we are about to explore are not fictional creations from science fiction novels. These were real projects, funded by actual military budgets, developed by scientists and engineers, and in many cases, tested in the field or prepared for combat deployment. What makes these weapons particularly fascinating is not just their oddity, but the serious military logic that drove their creation and the resources that nations poured into developing them. World War II stands out as perhaps the greatest period of experimental weapons development in human history. The scale of the conflict, the industrial mobilization of entire nations, and the desperate circumstances all combined to create an environment where military planners were willing to consider almost anything that might provide an edge over the enemy. The United States, with its vast resources and industrial capacity, explored some of the most unusual weapon concepts ever conceived. Among these were two projects that sound like they came from the pages of a comic book, yet they were taken seriously enough to receive substantial funding and development effort. The Bat Bomb project emerged from the mind of a Pennsylvania dentist named Little Adams, who happened to be a friend of First Lady Eleanor Roosevelt. In early 1942, just weeks after the attack on Pearl Harbor, Adams was returning from a vacation at Carlsbad Caverns in New Mexico. The cave system is home to millions of Mexican free-tailed bats, and watching these creatures pour out of the caverns at dusk gave Adams an idea that would soon reach the highest levels of the American government. Adams understood that Japanese cities, with their densely packed wooden structures, were extraordinarily vulnerable to fire. He also knew that bats were capable of carrying small loads while flying, could squeeze into tight spaces, and were naturally inclined to roost in attics and other dark spaces in buildings. Adams developed his concept rapidly. He envisioned capturing millions of bats, attaching tiny incendiary devices to them, placing them in refrigerated containers to induce hibernation, and then releasing them over Japanese cities at dawn. The bats would naturally seek shelter in the wooden buildings below, roosting in attics, under eaves, and in other hidden spaces throughout the structures. The incendiary devices, equipped with time-delay fuses, would ignite simultaneously, starting thousands of small fires across an entire city. Because the fires would begin in hidden spaces throughout the urban area, they would be almost impossible to fight effectively. By the time residents and firefighters discovered the flames, entire neighborhoods would be engulfed. What sounds like a far-fetched scheme actually received serious consideration at the highest levels. Adams managed to get his proposal in front of President Franklin Roosevelt himself, likely through the First Lady's intervention. Roosevelt found the idea intriguing enough to order the military to investigate its feasibility. In a memo that still exists in the National Archives, Roosevelt wrote that the idea looked like a perfectly wild idea, but was worth looking into. The National Research Defense Committee took up the project, designating it with the innocuous code name Project X-Ray. The military assigned the task to the Army Chemical Warfare Service, which began serious development work in 1943. The project team, working out of facilities in Texas and California, faced numerous challenges. First, they needed to determine which species of bat would work best for their purposes. After studying several options, they settled on the Mexican free-tailed bat, a species that was abundant, could carry a proportionally heavy load relative to its body weight, and had a wide natural range. These bats typically weigh about half an ounce, but can carry loads up to their own body weight. Engineers developed a specialized incendiary device for the project. The tiny bomb weighed just 0.6 ounces and consisted of a small capsule filled with kerosene gel, essentially a form of napalm. A time delay fuse made from a spring-loaded firing pin held back by a wire would trigger the device. The wire would corrode when exposed to air, and after a predetermined time, the pin would strike a small percussion cap, igniting the kerosene gel. The device was attached to the bat using a piece of surgical string and a clip that would attach to the loose skin on the bat's chest without significantly impeding its flight capability. The capture and handling of millions of bats presented its own set of problems. Teams of researchers traveled to caves across the Southwest, developing techniques to capture large numbers of bats without harming them. They discovered that cooling the bats to induce a state of torpor made them easier to handle and transport. This led to the development of specialized refrigerated containers that could hold thousands of hibernating bats. The containers, called bomb casings by the military, could be dropped from aircraft and were designed to open at a predetermined altitude, releasing their contents over the target area. Testing of the bat bombs revealed both the promise and problems of the concept. In one early test, at the Carlsbad Army Airfield Auxiliary Field in New Mexico, several bats escaped with live incendiary devices still attached. They flew to the base's buildings and promptly burned down a substantial portion of the facility, including a general's car and several newly constructed hangars. While this was embarrassing for the program, it actually demonstrated the weapon's effectiveness. The incident proved that bats would indeed roost in buildings, and that the incendiary devices worked as designed. More controlled tests followed at a specially constructed Japanese village mock-up at the Dugway Proving Grounds in Utah. The military had built this replica using authentic Japanese construction techniques and materials, creating a realistic target for testing various weapons. When bat bombs were tested against this mock village, the results were impressive. The dispersal pattern was excellent, with bats spreading throughout the structure complex and roosting in exactly the types of hidden spaces the planners had predicted. When the incendiary devices ignited, the resulting fires were devastating. Military observers noted that the bat bombs started more fires and caused more effective damage than comparable conventional incendiary bombs. A report from the Chemical Warfare Service noted that a single bat bomb could potentially start more individual fires than a conventional incendiary cluster bomb. The key advantage was dispersion and penetration. Conventional incendiary bombs tended to hit roofs and streets, where fires could be spotted quickly and firefighters could respond. The bat bombs infiltrated buildings, starting fires in hidden spaces throughout a target area, overwhelming firefighting capabilities through sheer numbers of simultaneous ignition points. Despite these promising results, Project X-Ray was eventually cancelled in 1944. The official reasons given included concerns about the time needed to bring the weapon into operational deployment and questions about its reliability compared to conventional weapons. However, the real reason was likely the development of a far more devastating weapon. By 1944, the Manhattan Project was making rapid progress toward developing an atomic bomb. Military planners recognized that nuclear weapons would render most other experimental projects obsolete. The Bat bomb, despite its demonstrated effectiveness in testing, could not compete with the destructive power of atomic weapons. Yet the Bat bomb was not the strangest guided weapon concept developed during World War II. That distinction arguably belongs to Project Pigeon, later redesignated Project Orkan, a program that attempted to use living birds as organic guidance systems for precision bombs. This project originated with B.F. Skinner, the renowned behavioral psychologist who had pioneered the study of operant conditioning. Skinner believed that his techniques for training animals could be applied to military problems, specifically the challenge of guiding bombs to precise targets. In the early 1940s, precision bombing was one of the most significant challenges facing military aviation. Bomb sights of the era were crude by modern standards, and hitting a specific target, even from medium altitude in perfect conditions, required considerable luck. Most bombs fell hundreds or even thousands of feet from their aim points. Bad weather, enemy fire forcing pilots to take evasive action, and the simple physics of dropping objects from moving aircraft at altitude all contributed to the problem. The military desperately wanted some way to guide bombs to their targets, but the electronic technology of the era was not up to the task. Radio-controlled bombs existed, but were primitive and unreliable. Radar guidance was in its infancy. What Skinner proposed was using nature's own guidance system, the sophisticated visual processing and motor control of the pigeon brain. Skinner's proposal was audacious in its simplicity. He would train pigeons to recognize specific targets, such as the profile of an enemy ship or the shape of a particular building. The pigeons would be placed in the nose of a bomb or missile, positioned in front of a screen showing the view ahead. When the pigeon pecked at the image of the target on the screen, sensors would detect the pecking and translate it into control signals that would steer the weapon toward the target. Multiple pigeons could be used in a single weapon, with their inputs averaged to improve accuracy and reliability. Skinner began preliminary work on the project with his own funds in 1940, training pigeons to recognize and peck at specific images. He developed a training protocol that used food rewards to condition the birds to respond to particular visual patterns. The pigeons proved remarkably capable. Using operant conditioning techniques, Skinner could train a pigeon to reliably recognize a specific target image in just a few days. The birds could distinguish between different shapes, respond to partial views of targets, and maintain their trained behavior even in stressful conditions. By 1943, the military had become interested enough to provide funding for a more serious development effort. The National Defense Research Committee allocated funds for what was officially designated Project Pigeon. Skinner assembled a team and set up operations in Minneapolis, where they worked to develop a practical weapons system. The technical challenges were considerable. The team needed to create a guidance system that could reliably detect pigeon pecks and translate them into control signals. They needed to design a capsule that would keep the birds alive and able to see and respond during the weapon's flight. They needed to solve problems of training, quality control, and reliability. The guidance system that emerged was ingenious. The pigeon would be placed in a jacket that held it in position in front of a small screen. A lens system would project the forward view onto this screen. The screen itself was made of a material that could detect the location of pecks. When the pigeon pecked at the image of the target, the position of the peck would be registered and used to generate steering commands. If the target appeared to the right of center, the pigeon would peck at the right side of the screen and the weapon would turn right. If the target moved left, the pigeon would peck left, correcting the course. The system was designed to be self-correcting, with the pigeon continuously adjusting the weapon's trajectory to keep the target centered. To improve reliability, Skinner designed his system to use 3 pigeons working in concert. Each bird would be in its own compartment, watching its own screen, but all 3 would be observing the same forward view. Their pecks would be averaged, so if one pigeon became confused or stopped responding, the other 2 would maintain guidance. This redundancy also helped smooth out random variations in individual bird behavior, producing steadier control inputs. The training program Skinner developed was sophisticated and effective. Pigeons would first be trained to recognize a basic target shape, such as a circle or rectangle, pecking at it to receive food rewards. Once they reliably responded to the simple shape, the training would gradually introduce variations, teaching the bird to recognize the target from different angles and distances. Eventually, the pigeons would be shown photographs or silhouettes of actual military targets, such as specific classes of warships or particular bridges or buildings. The training process took about 1 week per pigeon, and success rates were high. Most pigeons that entered training became reliable target recognizers. Testing demonstrated that the system worked. In laboratory conditions, Skinner's pigeons could guide a simulated bomb trajectory with remarkable accuracy. In one demonstration for military observers, a pigeon successfully guided a simulation toward an image of a battleship, making course corrections that would have resulted in a direct hit. The bird maintained its focus and continued to guide the weapon even when the experimenters introduced distractions and disturbances to simulate combat conditions. In other tests, pigeons trained to recognize specific bridges successfully picked out their assigned targets from aerial photographs that included multiple similar structures. However, Project Pigeon faced skepticism from the military establishment that ultimately proved insurmountable. Part of the problem was simply the strangeness of the concept. Many officers found it difficult to take seriously the idea of using birds to guide weapons. The image of pigeons sitting in the nose of a bomb, pecking at screens, seemed more like something from a cartoon than a serious military weapon. Skinner and his team gave several demonstrations to military committees, but these often backfired. Observers would watch the pigeons perform flawlessly in tests, then dismiss the entire concept as absurd. One committee member reportedly said that he could not recommend funding for a project that seemed so ridiculous, regardless of how well it worked in testing. There were also legitimate concerns about reliability under actual combat conditions. Would the pigeons continue to function when experiencing the extreme forces of a dive bomb attack? Would they be affected by the noise and vibration of anti-aircraft fire? What would happen to the guidance if the pigeons became frightened or disoriented? Could enemy countermeasures, such as bright lights or sounds, be used to confuse the birds? These questions were difficult to answer without full-scale testing, but the military was reluctant to invest in such testing given the inherent strangeness of the concept. The military cancelled Project Pigeon in 1944, concluding that other approaches to precision guidance showed more promise. However, the project was briefly revived after the war when the military became interested in developing guided missiles. In 1948, the U.S. Navy funded a continuation of the work, now redesignated Project Orkan, which stood for Organic Control. Skinner and his team refined their techniques and developed more sophisticated versions of the guidance system. They demonstrated that pigeons could control not just ballistic trajectories, but actively guided missiles, making continuous course corrections throughout extended flights. In tests, the pigeon-guided system achieved impressive accuracy, often performing better than early electronic guidance systems. Yet once again, the military ultimately abandoned the project. By the early 1950s, electronic guidance technology was advancing rapidly. While still primitive by modern standards, radar and early computer systems showed clear potential for development into reliable guidance systems. The pigeon approach, while it worked, represented a technological dead end. There was no clear path for improving or developing it further. Training and deploying millions of pigeons for military use presented logistical nightmares. The shelf life of a trained pigeon was limited. Quality control would be difficult. Electronic systems, despite their current limitations, offered a clear development path toward better performance and greater reliability. Project Orkan was permanently cancelled in 1953. Looking beyond these American projects, other nations developed their own strange weapons during World War II and other conflicts. The Soviet Union, facing desperate circumstances during the Nazi invasion, developed anti-tank dogs. This weapon system, if we can call it that, was one of the most tragic and ultimately unsuccessful experiments in animal warfare. The concept was simple in theory, but proved deeply flawed in practice. Dogs would be trained to find food under tanks. After extensive conditioning, they would associate the underside of tanks with food rewards. In combat, the dogs would be fitted with explosive packs and released toward enemy tank formations. The idea was that the dogs would run under the tanks seeking food, at which point the explosives would be detonated, either by a timer or by a trigger that activated when the dog went under the tank. The Soviet military trained thousands of dogs for this purpose starting in the late 1930s. Special training schools were established, and considerable resources were devoted to the program. However, the system failed in almost every possible way when deployed in actual combat. The dogs had been trained using Soviet tanks, which ran on diesel fuel. German tanks used gasoline. The dogs, accustomed to the smell of diesel, were confused by the different odor and often ran towards Soviet tanks instead of German ones, or simply ran away from the battlefield entirely. The noise, chaos, and terror of actual combat overwhelmed the dogs' training. Many would panic and run in random directions, sometimes returning to friendly lines with their explosives still attached. German tank crews quickly learned to machine gun any dogs approaching their vehicles, and the dogs' natural fear response to gunfire meant that survivors would flee. In several documented cases, the anti-tank dogs caused casualties among Soviet troops, either by detonating near friendly positions or by panicking entire units when dogs with explosives ran through their lines. The program was officially ended in 1942, though some units continued to use anti-tank dogs through 1943. Later estimates suggested that only a handful of German tanks were ever destroyed by anti-tank dogs, while the program consumed significant resources and caused considerable friendly fire casualties. The Germans themselves developed unusual weapons, including one of the most notorious of World War II, the V-1 flying bomb. While the V-1 was not as bizarre as bat bombs or pigeon-guided missiles, its guidance system was remarkably primitive yet effective. The V-1 was essentially a pilotless aircraft, a precursor to modern cruise missiles. It was powered by a pulse jet engine that produced a distinctive buzzing sound, leading British civilians to call it the buzz bomb or doodlebug. The weapon was cheap to produce compared to conventional aircraft, and could be launched from simple ramps rather than requiring airfields. The V-1's guidance system consisted of a gyroscopic autopilot that kept the weapon flying straight and level, a magnetic compass that kept it pointed toward the target, and a simple mechanical counter that measured the distance traveled. A small propeller in the nose spun as the weapon flew, with each revolution counted by the mechanism. When the counter reached a preset number corresponding to the distance to the target, it would trigger the diving mechanism, pushing the V-1 into a steep dive toward the ground. The system was crude and subject to numerous sources of error. Wind could push the weapon off course. The counters were mechanical and could malfunction. Manufacturing variations meant that no two V-1s flew exactly the same profile. Despite these limitations, the V-1 was terrifyingly effective as a terror weapon. Germany launched over 10,000 V-1s at targets in England and Belgium between 1944 and 1945. The weapons killed over 6,000 people and wounded nearly 18,000 more. The psychological impact was severe. The distinctive sound of the pulse jet engine meant that people could hear the weapons approaching, and everyone learned that when the engine cut out, the bomb was beginning its dive and detonation was imminent. This gave people just seconds of warning, enough time to feel terror, but often not enough time to reach shelter. The randomness of the weapons added to the psychological toll. They could hit anywhere within a large target area, and there was no way to predict where any individual V-1 would strike. The British developed increasingly sophisticated defenses against the V-1, including anti-aircraft guns, barrage balloons, and fighter aircraft specially trained to intercept the bombs. Fighter pilots developed a technique where they would fly alongside a V-1 and use their wingtip to flip the bomb's wing, sending it into an uncontrollable roll and crash. This was incredibly dangerous, but was sometimes preferred to shooting at the V-1, which could detonate its warhead in an explosion that might destroy the fighter aircraft. By the end of the campaign, British defenses were destroying about 80% of V-1s before they reached their targets, but the 20% that got through still caused significant damage and casualties. Germany followed the V-1 with the V-2 rocket, a weapon that was far more sophisticated technologically but equally indiscriminate in its targeting. The V-2 was the world's first long-range ballistic missile and represented a tremendous leap in rocket technology. It could travel at supersonic speeds, reaching altitudes of over 50 miles before plunging down onto its target. There was no defense against the V-2. It moved too fast for interception, and it struck without warning, as the weapon traveled faster than sound and would impact before the sound of its approach could be heard. However, the V-2's guidance system was only marginally more sophisticated than the V-1's. It used gyroscopes and an early analog computer that shut off the rocket engine when the weapon had reached the correct velocity to hit a target at a predetermined range. The accuracy was poor, with the weapon having a circular error probable of about 10 miles. This meant that half of all V-2s would land within 10 miles of their aim point, but the other half would land even further away. The weapon could only hit area targets like cities. It could not be used against specific military installations or strategic targets. Like the V-1, it was essentially a terror weapon. Germany launched over 3,000 V-2 rockets during the war, killing roughly 7,000 people. However, the program consumed enormous resources. The rockets were expensive to produce and required sophisticated manufacturing facilities and rare materials. The underground factory where many V-2s were built, using slave labor from concentration camps, was itself the site of a humanitarian catastrophe, with more people dying in its construction and operation than were ever killed by the weapons it produced. From a military standpoint, the V-2 program was arguably counterproductive, consuming resources that could have been used for more effective weapons. The Japanese military developed several unusual weapons, driven by a combination of technological limitations and the desperate circumstances they faced by the later stages of the war. The Chiton was a manned torpedo, essentially a suicide weapon. It was based on the Type 93 torpedo, known to the Allies as the Long Lance, which was one of the most effective conventional torpedoes of the war. The Chiton added a small cockpit where a pilot would sit, steering the torpedo toward enemy ships. The pilot could make course corrections throughout the attack run, theoretically improving accuracy compared to conventional torpedoes. In practice, the Chiton was a death trap that achieved limited results. The pilot sat in a cramped, poorly ventilated space with only a small periscope to see the outside world. Steering was difficult, and the pilot had no way to escape once the attack began. Of the several hundred Chiton attacks launched during the war, only a handful achieved any success. Most missed their targets entirely or suffered mechanical failures. American defenses also proved effective at detecting and destroying Chiton before they could reach their targets. The submarines that carried and launched Chiton were themselves vulnerable during launch operations, and several were sunk while preparing or conducting Chiton attacks. The Nakajima Kicker was Japan's attempt to develop a jet fighter late in the war. By 1945, Japan was aware of German jet aircraft development and was attempting to produce its own jet-powered planes. The Kicker bore a superficial resemblance to the German Me-262 jet fighter, though it was actually a completely independent design. Only 2 prototypes were completed before the war ended, and the aircraft never saw combat. However, plans existed to use the Kicker as the basis for suicide attack aircraft, continuing Japan's desperate strategy of trading pilot lives for ship kills. Perhaps the strangest Japanese weapon was the Fugo balloon bomb. This weapon represented an innovative but ultimately ineffective approach to attacking the American mainland. Japan launched approximately 9,000 balloons carrying incendiary and high-explosive bombs between November 1944 and April 1945. The balloons were made of paper derived from mulberry bushes, chosen for its strength and ability to hold hydrogen gas. Each balloon was about 33 feet in diameter when fully inflated. The ingenious part of the Fugo was its altitude control system. The balloons were designed to ride the jet stream across the Pacific Ocean, a journey of roughly 5,000 miles that would take about 3 days. To maintain the correct altitude throughout this journey, each balloon carried a set of sandbags as ballast and an ingenious barometric trigger mechanism. If the balloon descended too low, the mechanism would automatically release ballast, allowing the balloon to rise. If it rose too high, a valve would release hydrogen. This system allowed the balloons to maintain an altitude of about 30,000 feet throughout their trans-Pacific journey. When the balloons reached North America, another timer mechanism would release the bombs and destroy the balloon itself to prevent it from being captured and studied. The bombs were a mix of incendiaries designed to start forest fires and high explosives designed to kill people and destroy property. The Japanese military hoped that the balloons would start massive forest fires across the Pacific Northwest, divert resources to firefighting and air defense, create panic among the civilian population, and generally disrupt the American war effort. The campaign failed to achieve any of these objectives. The timing was unfortunate for Japan, as the balloons arrived during winter when forests were wet and unlikely to burn. American authorities imposed a news blackout on the balloon bombs, so there was no panic, and the Japanese had no way of knowing whether their weapons were even reaching the American mainland. This lack of information led them to conclude that the campaign was failing, and they ended it after only a few months. In reality, several hundred balloons did reach North America, landing across a wide area from Alaska to Mexico and as far east as Michigan. The only casualties from the balloon bombs occurred in Oregon in May 1945, when a pregnant woman and 5 children encountered a balloon bomb that had landed in the forest. The woman's husband, a minister, had driven them to a picnic area for an outing. While he was parking the car, his wife and the children went ahead into the woods. They found what appeared to be a large paper ball and began examining it. The bomb exploded, killing all 6 of them instantly. These were the only combat deaths on the American mainland during World War II. The incident remained classified for the duration of the war to maintain the news blackout on the balloon bombs. Moving beyond World War II, the Cold War era saw its own share of bizarre weapons proposals. The United States developed several remarkable and sometimes frightening concepts during this period. Project Plowshare was a program to develop peaceful uses for nuclear weapons. The idea was that nuclear explosives could be used for massive earth-moving projects, such as excavating harbors, creating canals, or even using the explosions to extract natural gas from deep rock formations. Numerous underground nuclear tests were conducted as part of this program between 1961 and 1973. Some of the proposals were staggering in their scope. One plan called for using nuclear explosions to create a new sea-level canal across Central America as an alternative to the Panama Canal. Another suggested using nuclear explosives to create a harbor in Alaska. The most ambitious proposal involved using nuclear weapons to redirect rivers in Alaska and Canada, creating a massive water management system that would irrigate arid regions and generate hydroelectric power. None of these grand projects were ever implemented, partially due to environmental concerns and partially due to growing awareness of the dangers of radioactive fallout. The most unusual deployment of Project Plowshare technology was Operation Plowshare, which was actually a natural gas stimulation project in Colorado in 1969. A 40-kiloton nuclear device was detonated 8,400 feet underground to fracture rock formations and release trapped natural gas. The explosion created a cavity about 300 feet in diameter and fractured rock throughout a large volume. Natural gas did flow into the cavity and was extracted and tested. However, the gas was contaminated with radioactive isotopes, making it commercially unusable and potentially dangerous. The project demonstrated the technical feasibility of nuclear fracking, but also revealed its fatal flaw. The economics and safety concerns meant that no further nuclear stimulation projects were attempted. The U.S. Air Force studied several concepts for nuclear-powered aircraft during the 1950s and 1960s. The idea was that a nuclear reactor could provide essentially unlimited flight endurance, allowing bombers to remain airborne for days or even weeks. This would make them invulnerable to surprise attack, as they would not be sitting on airbases where they could be destroyed. The technical challenges were immense. A nuclear reactor for an aircraft needed to be light enough to fly, but heavily shielded enough to protect the crew from radiation. It needed to be reliable enough to operate safely in flight and safe enough that a crash would not cause a nuclear disaster. The aircraft nuclear propulsion program ran from 1946 to 1961 and cost over $1 billion. Engineers developed and tested several reactor designs. One test aircraft, a modified B-36 bomber, actually flew with a small operational reactor on board. However, the reactor did not power the aircraft. It was simply carried along to test whether a reactor could operate safely in flight. The tests revealed numerous problems. The shielding required to protect the crew was extremely heavy. Ejection seats could not be used because the crew needed to be surrounded by shielding. The reactor coolant was corrosive and difficult to work with. If an aircraft crashed, the reactor could breach and spread radioactive contamination over a wide area. Ultimately, the program was cancelled when advances in aerial refueling technology made it unnecessary. With aerial refueling, conventional aircraft could remain airborne for extended periods by meeting tanker aircraft periodically. This approach was far simpler, safer, and cheaper than nuclear propulsion. The development of ballistic missiles also reduced the need for long-range bombers. The only tangible legacy of the program was the development of the Convair NB-36H test aircraft and significant advances in nuclear reactor technology that would later benefit naval nuclear propulsion programs. The United States also experimented with biological weapons during the Cold War era, though these programs were officially ended in 1969. Some of the work involved developing weapons that could specifically target crops, with the goal of causing famine in enemy nations. The rationale was that destroying an enemy's food supply could be strategically valuable, while theoretically causing less immediate loss of human life than conventional weapons. However, the ethical problems with deliberately causing famine proved overwhelming, and these weapons were never deployed. The Soviet Union developed their own array of unusual weapons. The Caspian Sea Monster was a massive ground effect vehicle, an aircraft designed to fly just a few meters above the surface of water, riding on a cushion of compressed air. These vehicles, officially called ekranoplanes, could carry heavy loads at high speeds while being difficult to detect by radar. The Lung-class ekranoplan, completed in 1987, was armed with 6 large anti-ship missiles and was designed to attack NATO naval task forces. The single completed example was impressive, measuring 240 feet long and weighing 380 tons at full load. However, the concept proved impractical. The vehicles were difficult to pilot, could only operate over water, were vulnerable to bad weather, and offered no clear advantages over conventional aircraft or ships. The program was abandoned after the fall of the Soviet Union. The AK-630 close-in weapon system represented a more practical Soviet innovation, though its rate of fire was so extreme that it seemed almost absurd. This automated gun system, designed to defend ships against incoming missiles, consisted of 6 rotary cannons that together could fire 5,000 rounds per minute. The system used radar to track incoming threats and could engage multiple targets simultaneously. While not as unusual in concept as some weapons we have discussed, the sheer volume of fire it could produce, essentially creating a wall of metal in the air, represented an extreme approach to the missile defense problem. Chemical weapons represent another category of unusual warfare. While they had been used extensively in World War I, several nations continued to develop and stockpile them during the Cold War, despite international agreements. The Soviet Union developed Novichok agents, an extremely toxic class of nerve agents, in the 1970s and 1980s. These weapons were specifically designed to be undetectable by standard NATO chemical detection equipment and to be resistant to standard chemical weapon antidotes. The program was kept secret even from most of the Soviet government, violating international chemical weapons treaties that the Soviet Union had signed. In more recent conflicts, improvised weapons have sometimes been as unusual as anything developed in government laboratories. During the Syrian civil war, various factions used improvised mortars made from gas cylinders, launched using black powder charges. These weapons, called hell cannons by some fighters, were wildly inaccurate but psychologically intimidating due to their size and the massive explosions they produced. They represented a return to siege warfare tactics not seen since previous centuries, adapted with modern materials. Returning to World War II, another unusual American project deserves mention. The Bat glide bomb was an early guided missile that actually saw combat use. Unlike the pigeon-guided bombs, the Bat used radar to home in on targets. The weapon was carried under the wing of patrol bombers and released while the aircraft was still miles from the target. After release, the Bat would glide toward the target area while its radar seeker scanned for the largest metallic object, which it would lock onto and guide toward. The weapon was used successfully against Japanese ships in 1945, achieving several hits and proving that guided weapons could work in combat. The name Bat was derived from the weapon's ability to find targets in darkness, like the animal it was named after, though unlike Project X-ray, it did not actually use any bats. The Germans developed the Fritz X guided bomb, which was radio-controlled rather than autonomous. A bombardier in the launch aircraft would watch the bomb fall and transmit steering commands via radio, guiding it toward the target. The system required the launch aircraft to remain in the area throughout the bomb's flight, making it vulnerable to enemy fighters and anti-aircraft fire. Despite this limitation, the Fritz X achieved notable success, including sinking the Italian battleship Roma in 1943. This was one of the few examples of a battleship being sunk by air-launched weapons during the war. Acoustic homing torpedoes represented another unusual guidance concept. Rather than requiring the submarine commander to calculate a precise firing solution, these torpedoes would simply follow the sound of a ship's propellers. The first acoustic torpedoes, developed by Germany, entered service in 1943 and achieved some success. However, the Allies quickly developed countermeasures. Ships began towing noisemakers behind them, creating louder sounds than their own propellers and attracting torpedoes to these decoys instead. The technology eventually became more sophisticated and reliable, forming the basis for modern anti-submarine homing torpedoes. Mines have been used in warfare for centuries, but World War II saw the development of unusual new types. Oyster mines were a class of naval mine that responded to changes in pressure rather than direct contact or magnetic fields. When a ship passed over an oyster mine, the change in water pressure would trigger detonation. This made them almost impossible to sweep using conventional methods. The Germans deployed these mines in the shallow waters around Normandy before D-Day, causing significant casualties among Allied vessels. The British developed similar weapons called influence mines that could respond to various physical phenomena, including pressure, sound, and magnetic fields. Landmines also became more sophisticated and deadly. The German S-mine, called the Bouncing Betty by Allied soldiers, was particularly feared. When triggered by a tripwire or pressure plate, a small charge would launch the main mine body about 3 feet into the air. A second later, the main charge would detonate, spraying metal fragments horizontally at roughly waist height. This design maximized casualties by directing the blast into the most vulnerable parts of the human body and extending the lethal radius compared to surface detonating mines. The psychological effect was significant, as soldiers knew that triggering one of these mines gave them just a second before detonation, not enough time to escape or take cover. One of the strangest German weapons was the Krumlauf, a curved barrel attachment for the STG-44 assault rifle. The device used a series of mirrors and a bent barrel to allow soldiers to shoot around corners without exposing themselves to enemy fire. The bent barrels came in several configurations, with bends of 30, 45, or even 90 degrees. In practice, the weapons were nearly useless. The curved barrels wore out extremely quickly, often splitting or bulging after firing just a few dozen rounds. Accuracy was poor because the bullets tumbled when exiting the bent barrel. The optical system was fragile and difficult to use in combat conditions. A few were produced and issued to troops fighting in urban environments, and to tank crews who needed to defend against infantry approaching their vehicles, but they saw limited use. The Japanese Fujita plan involved using submarine-launched seaplanes to drop incendiary bombs on forests in the Pacific Northwest. The goal was similar to that of the Fugo balloon bombs, starting massive forest fires that would divert American resources and spread panic. In September 1942, a Japanese submarine surfaced off the coast of Oregon and launched a small seaplane. The pilot dropped 2 incendiary bombs on a forested area near Brookings. The bombs failed to start any significant fires due to damp conditions from recent rain. The attack remains the only aerial bombing of the continental United States by a foreign military during World War II. A second attack a few weeks later also failed to cause significant damage. The plan was abandoned as it became clear that seaplanes launched from submarines could not carry enough ordnance to cause meaningful damage. The Japanese also developed the Yokosuka MXY-7 Oka, a purpose-built kamikaze aircraft. Unlike conventional planes adapted for suicide attacks, the Oka was designed from the outset to be a piloted missile. It was essentially a flying bomb with a cockpit, carrying a massive 2,600-pound warhead. The aircraft had stubby wings and 3 rocket engines that could propel it to speeds over 600 miles per hour in its final dive. It was carried underneath a bomber aircraft and released within range of enemy ships, at which point the pilot would ignite the rockets and guide the weapon toward the target. The Oka was deadly if it reached its target, but suffered from severe operational limitations. The bomber carrying it was slow and vulnerable, especially with the drag and weight of the Oka attached underneath. American fighters learned to target these heavily laden bombers before they could release their weapons. Of the approximately 850 Oka aircraft built, only a small fraction were actually used in attacks, and only a handful of those scored hits. American sailors called the weapon baka, the Japanese word for fool, reflecting their view of both the weapon and the tactics it represented. Throughout all of these examples, we see common themes emerging. Desperation often drives unusual weapons development. Many of the strangest weapons came from nations facing defeat or existential threats. Japan's various suicide weapons became more prevalent as their strategic situation deteriorated. Germany's wonder weapons were developed during a period when conventional approaches were clearly failing. The bat bombs and pigeon-guided missiles emerged from America's early war period, when the ultimate outcome was still uncertain, and every possible approach needed exploration. Another theme is the gap between theoretical promise and practical performance. Many unusual weapons worked well in controlled testing, but failed in actual combat. The conditions of real warfare, with its chaos, unpredictability, and enemy countermeasures, often exposed flaws that laboratory testing had not revealed. The anti-tank dogs that ran toward the wrong tanks, the balloon bombs that arrived during wet weather, the Krumlov barrels that split after a few shots, all represented ideas that seemed sound in theory, but collapsed when confronted with reality. Cost-effectiveness is another recurring issue. Even when unusual weapons worked as intended, they often consumed resources disproportionate to their military value. The German V2 program channeled enormous resources into a weapon that killed relatively few people and hit no militarily significant targets. The nuclear aircraft program consumed $1 billion without producing a practical weapon. The bat bombs demonstrated effectiveness, but required complex logistics and training that made them impractical compared to conventional incendiaries. Yet some unusual weapons did prove their worth or led to important technological developments. The Bat glide bomb and Fritz X guided bomb pioneered concepts that would eventually mature into modern precision-guided munitions. Research into rocket weapons, even when the specific applications failed, contributed to the development of space launch vehicles and ballistic missiles. The study of animal cognition and behavior, driven by projects like the pigeon-guided missiles, expanded scientific understanding, even if the military applications did not pan out. These weapons also reveal something important about human nature and warfare. When faced with threats to survival, humans will explore any possibility, no matter how strange or seemingly absurd. The scientists and engineers who worked on these projects were not foolish or incompetent. They were often brilliant individuals making rational decisions within the constraints and knowledge of their time. What appears bizarre in hindsight often made sense given the circumstances, available technology, and understanding of the era. The legacy of these unusual weapons extends beyond their immediate military impact. They represent experiments in the possible, explorations of the boundaries of what could be achieved. Some ideas proved to be dead ends, interesting concepts that ultimately led nowhere. Others planted seeds that would eventually grow into important technologies. The guided weapons of World War II, whether using pigeons or primitive electronics, were ancestors of modern cruise missiles and smart bombs. The lessons learned from failures, like the nuclear aircraft program, informed later successful projects in nuclear engineering. These weapons remind us that warfare has always been a driver of technological innovation, for better and worse. The desperate circumstances of war push societies to explore options they would never consider in peacetime. The moral implications of these developments deserve consideration as well. What does it say about humanity that we will strap explosives to dogs, train pigeons to guide missiles, and contemplate creating massive forest fires to achieve military objectives? These questions become even more pointed when we consider that all of these weapons were developed by democracies fighting against genuinely terrible threats, not by totalitarian regimes with no regard for ethics. The strange weapons of history serve as cautionary tales as much as curiosities. They show us how easily resources can be misdirected, how compelling ideas can fail in practice, and how desperation can lead to choices that seem absurd in retrospect. Yet they also demonstrate human ingenuity, creativity, and the willingness to explore unconventional solutions to difficult problems. Whether we judge these weapons as brilliant innovations or terrible mistakes often depends on our perspective and the passage of time. What remains certain is that as long as warfare exists, humans will continue to develop new and sometimes bizarre ways to fight, exploring every possible advantage, no matter how unusual it might seem.